Okay, so just okay, please just raise your hand if you have a USB key and you finished copied it, or ask around you to people who need it. Okay, so on the VM, there is one folder in the home directory of the user. The user is user with password user. If you need, okay, just I think someone. Everything is in the home folder RIOT course, and inside this directory you have two directories, or several directories, but you have a RIOT clone, a clone of the RIOT source code from the latest release, and you have exercises directory with different exercises that we will work on during the tutorial. We won't work on all the exercises, but so as I said already, there are all development tools already installed. Most important is the ARM toolchain. We work on ARM STM32L0 based board. You have IoT-Lab command line interface tools already installed, and I installed a few editors. So I hope I will reach most of the favorite stuff. Like Emacs, my favorite one, which is the Visual Studio Code.
You have the VM already?
No. I have a VM for you if you want.
What is the VM?
Okay. So a few words on IoT-Lab. If you don't know IoT-Lab already, it's a large-scale experimentation testbed, and it can be used for testing wireless communication protocols. You can access remotely to nodes with radios, like 15.4 radios. So people do IPv6 on microcontrollers for some of the stuff that we saw yesterday. But now we can also work with LoRa, and that's the node that we will use today. They can be used to learn IoT programming and communication protocols, or you can just use them to test your software platforms. And it was used by Gaetan during the last release cycle to test RIOT before the release. So here you have an idea of the hardware that we have, not only this, which is a second part, and the different sites, IoT-Lab sites, that are distributed in the regions. And so where I work, there is one IoT-Lab site, which is the Saclay site, and this is where we will book nodes today. So Saclay is the only site with LoRa nodes for the moment. Okay, so in short, we have more than 2,000 programmable nodes with 4 architectures. Here we have a list of available platforms. So most of them are just using or providing 15.4 communication, and the ST board is for the LoRa part. So heterogeneous radios, and so soon we'll also have a BLE node, so based on Nordic NRF52. So the principle of IoT-Lab is similar to the previous slide, but you are here on your computer. You have a website where you can control an experiment, and you have sites with a SSH frontend that you can connect to. And from the SSH frontend, you can access to nodes using a TCP connection that redirects the serial port of the node. That's the principle. This is what we will use today. So the idea is you are on your computer, you flash a firmware, and you can send the firmware via HTTP to each site to control the node of the site. Okay, so the best with IoT-Lab is to start learning it. So we have a big list of tutorials for almost everything. So you can do this morning. It takes, I think it takes 2 full days to play all of them. Okay. So does everybody have the VM? Who don't have the VM setup? You don't? You want it?
It's fine. Okay.
Okay, so the first steps with the VM is to follow what is explained here. So you start it, and you open the command window. So the paper with the IoT-Lab account is this. So each account or RIOT Summit with a number, and the second column is the password. So those are demo accounts. I will remove them in the coming days, but you can just use them this morning. Yes, it's configured with French keyboard. Sorry. But you can easily change it from the. Okay, so the third step is to register your IoT-Lab credentials inside the VM. So there is a tool to do it. What it will do is just it will write the password in a file somewhere, and then each time you will access the REST API of IoT-Lab, they will be used to interact with the HTTP REST API. So this is the initial step. And the fourth step, you will start an experiment in IoT-Lab. So you will book one node, and it will give you, it will select one of the available nodes. So you don't choose the exact node that you want. The system will select one for you. You wait for the experiment to be in the running state. So when you are in the running state, you have somewhere in IoT-Lab a node that is powered on that you can access to. And to know, so is it okay for everyone here? So you can follow the slides as well on the local. So how to know the node that was booked automatically by the system for you? There is a command for that. So you can get -e, which is the identifier of the experiment, and -r is for resource, and it drops a JSON stuff, and you have this field network address that gives you the full name of the node that is for you. So here it is st-1-10.saclay.iot-lab.info, but for you it will be a different one, or maybe this one exactly, because you are the winner. Okay, so you have to remember this because you will use it during the tutorial with the RIOT build system to flash and open a terminal on it. Okay? So there is a very good integration of IoT-Lab in the RIOT build system, and you will be able to notice that. So if you have questions, don't hesitate to ask. So is it okay here? Questions? Problems? Okay, so once you are done with what I presented just before, you can switch to the Getting Started section of the RIOT course, and we will follow it together. Okay. Any questions? Any problem? We can continue here. So we're getting started. So if yes, okay. So getting started with Riot. So there is some prerequisites, but we won't follow them because the VM has already everything in it. Okay. So it will take a bit of time. So first, for those who never wrote or built a Riot application, what is a Riot application? It just consists in two files at the very minimum state. So you have the make file that describe several variables, minimum variables, and include the Riot-based makefile.include. And in this file, you have all the targets and other inclusion that's done. So I don't recommend for people who are not very confident with Make to start looking at the makefile.include of Riot. It's not the best thing to do because it's very complex. So you can see you have application, this is the application name. It will be given to the generated firmware file. So you will have application.elf or the application.x created somewhere. The board, so this is the target for which you are building your application. So by default, here it's native. Native means you are building with a regular GCC, so you are creating a regular Linux process. But here you can change to any board supported by Riot. And the build system will automatically select the right toolchain for you. So the ARM, known, the Abedie, GCC, stuff like that. The Riot base is just saying the base directory of Riot is there. So since this application is, okay, so it's just pointing to the right Riot directory. And then the second file is the C file where you just write your main function. So the entry point so you will jump at the startup of the application in the main function. Well, I don't describe the structure of a Riot application in detail. There are other slides in the course that does that. So you won't go. So as you can see here, it's very simple. It's a standard C programming. You can reuse standard include. You have puts functions that are part of the standard library. It's not like Arduino with print ln or something like this, which is not really standard. Okay. So the Riot build system is based on Make, as I said. So when you want to build an application, I remember the first time I discovered Riot, I thought, okay, I clone Riot and I do make at the base directory. I do make at the base directory, and it was saying, hey, you are not calling make at the right place. So I was a bit surprised. It was very strange for me. In fact, if you want to build an application, you have to go inside the application directory and run make from there. So this can be done in two ways. First way, so you cd to change directory to there, or you can use the -c parameter of make with the given directory. So this is what I'm using personally. So I cd to the Riot-based directory, and then if I want to build an application, make -c directory to the application, and it's done. Okay, so you can use, as I said, the board variable to specify the target at build time. And if you want to have a list of boards supported by Riot, you can have a look into the Riot source code boards, and you have a full list of boards supported by Riot. So more than 120, I don't have. And you can specify the Riot-based variable to specify. Say, okay, once you have built your application, you can run it. If you select the native, it creates a regular Linux process that you can run directly. And if you want to run on hardware, there is another phase that is required, is to write the generated firmware on the flash memory of the board and reset the board. Okay. So this can be done with the flash and term targets with Make. So Flash will build and write the firmware on the microcontroller flash memory, and Term will just open the terminal connecting to a serial port of the board, and then everything that is printed by the firmware arrives via this connection. And this can be done in one command. And you can also use the same command with the native. So Flash will just execute, will rebuild the firmware, and will do nothing in native. So example of the output of the build, okay? And there is your first exercise. So you can go there and build your first application. Nothing to change, just run the commands. So questions at this point? You have a question? So when you build the application, what it does? If you just look through all the required modules or parts that need to be built in your application, so here you have a path, and you can see that it goes in boards native drivers to build the required drivers for the native platform. Then it goes into the core, like in core you have the core OS system, so the kernel of RIOT, and other things like inter-process communication things and stuff like that. Then it goes to the CPU, so to know what is needed by RIOT to control the CPU, the drivers and the system. So here we have auto-initialization thing. And it generates at the end, you see the line where it creates my first app.elf file, and this is the RIOT application just built by me. And you can run it directly. It's just a Linux process. So I'm running it on my laptop. Okay. And it displays a few things like a welcome message, So you have some emulated LED thing, and it prints a message, my first RIOT application. So to quit the application, you just do Ctrl+C. Okay, so this is the interesting part of this step, because we will redo it a lot during the tutorial. It's built and run for the hardware. Okay, this is what we will use with IoT-Lab. So here, you call the same command, but this time you do board EL. So you specify which specific hardware target you want to use for when you build. And you can see that the output is a bit different. It's using a different board. It's using CPU like STM32 thing, so to build what is required for the STM32 CPU that is on this board. And then it does a lot of, it takes other system libraries. So you can check the type. It's an ARM. It's not a x86 application. It's an ARM application, so it's not the same architecture. But now, if you want to flash it on the node, since we are using IoT-Lab, you have to pass another variable, which is IoT-Lab node, with the name of a node that was booked by the IoT-Lab reservation system. So behind the hood, under the hood, the build system of RIOT will call the tools, the flashing tool of IoT-Lab, instead of calling the regular flashing tool that you use when you have a board plugged on your computer. So there is a bit of magic behind that. So if you use this command with this part at the same time, it will build and flash and open a terminal to a board that is somewhere in France, in the south of Paris. Okay. So everyone has reached this step? Any problem with this part?
Where I can find the graph that you just showed in 4.
The main file is directly.
Yeah, yes.
I used to separate the
From this side, it's camera. But if you want my
the same way with the red folders in this case. We left the RIOT exercise, but you can, as long as you connect this RIOT base to where your RIOT directory is, it should work. And,
which is quite awesome when you think of all the stuff that are hidden behind all this workflow. But, okay, so we can continue to the next step. Okay, so at the bottom of the README, you have a link to the next slide of getting started. We want to extend our application, because here is really a very basic application with almost nothing in it. It just prints a message on the STD.io of the application. But what we would like to do is do more things with RIOT. And how can we do that? You can extend your application with different ways by adding other variables in your main files. So you can use extra modules with a use module variable. So xtimer is an extra timer which is built on top of hardware timers, but with a lot of features. The FMT module allows you to format strings, because we all know that formatting strings in C is a hell. And you have the shell module that we will use after in the next exercise. The PS that allows you to print the status of the kernel, the different threads running in your application, and many others. You can also include external packages. So a package is using another project or external sources, and when you build your firmware, it clones automatically this source, it patches on the fly, and add it in the firmware. So this allows you don't need to put everything into Riot, you can just write a few makefile code to give different rules to prepare your package. And like this, we have LWIP network stack, or the Semtech lorawan stack that we will use later in the tutorial, if we can reach it. And the features required, that are features that come from the microcontrollers, so very low-level stuff like GPIO, UART, SPI, and many others. So what does it look like in your makefile? It's just use module plus equal, and then you add to the list of modules that will be built in your application. So the more modules you put in your application, the bigger your firmware will be at the end. But you have you can select precisely what you really need and what will be built in your final application. You can also add extra modules from the command line using this kind of so you pass variable environment variable to the make command. Okay, so can be useful with auto init things. Okay, and the next exercise is to add shell capability to your application and start interacting with the firmware from the command line.
Oh, okay. Oh, sorry. Oh, like this. Okay, so I'll come back.
I think I forgot something to say. In the exercise directory, you need to git pull origin master to fetch the latest version of the exercises, because we wrote them a lot during the last days. Yeah, you need to fetch the latest version. Otherwise, we won't have all the things, or we'll be missing.
Yeah, yeah. shell.
Yeah.
So, I think most of you could reach the shell application from on the board in IoT-Lab and start typing the help command. So you have an empty shell. If you add other modules, you can, like, for instance, if you add this shell commands module, it will add to the firmware a few commands that are predefined in RIOT, like just the reboot. So you can reboot the node from the shell. But if you add other modules, like the PS module, you will have a new command called PS, and you can have an overview of the running threads in your application. So the exercise, if you want to move fast, we have a solution and a subdirectory, dot solution subdirectory. So you need to pull the last version, but if you do that, when this is done, you have a solution with full exercise, with full source code. It's not the solution, it's one of the solutions. Okay, we will have to move a little bit faster. So it's not very important to write your own handler. You can just look at the solution afterwards. So the question now is the last part of the beginning of the tutorial. I mean, after that we will do LoRa. It's how to interact with the hardware into RIOT. You have so the interaction with the hardware can be done at three levels. First level is at the board level. So in the board there are some macro defined to access LEDs or buttons. So it's just pins to the MCU. This is you can use them just by including the board.h file. The second level is directly at the CPU level. So you have APIs to access the peripheral that are in the CPU. So the I2C, UART, SPI. Okay. So this is considered as the hardware abstraction layer of RIOT, in the sense that it's the same API that you can use on any kind of microcontrollers. So, it can be either AVR or STM32, Atmel, Kinetis, and other things. Many others, and recently ESP8266. Okay, and the third level is high-level drivers that are built on top of this abstraction layer to access sensors, actuators, or radio devices. So it's just a matter of importing the module BMP180 or HTS221, the one that we use later, or the SX1276, LoRa radio. And you have access, so inside those drivers you have calls to the hardware abstraction layer of RIOT, making theoretically the drivers hardware agnostic, which in real life is not always the case, because You can have things with GPIOs. So the next exercise is to, so the first part of the exercise, playing with the LED, you can skip it. Just go directly to the sensor exercise, okay? So in this exercise, the idea is to use the I2C sensor that is plugged to the LoRa board just to read temperature and relative humidity values, okay? So there is an example application already available in the RIOT code base. It's in a test. The exercise invites you to reuse this and to write shell commands to write the temperature and relative humidity. Okay? So once you have done that, we will switch to the LoRaWAN part of the tutorial. So I will come to help you if you have questions.
No, skip. Yeah.
So skip the LED exercise. Go directly to the sensor exercise.
Yeah.
Okay. And you have, if you really want, if you are very impatient, you can go directly to the, you can have a look at the dot solution directory, where I wrote some stuff. So it goes like this. Most is copy pasted from the test application that is already provided by RIOT.
And then you can like this. This board has LEDs on it.
Maar dat valt wel mee met het punt gewoon dat je eigenlijk een tool moet hebben of Nee, we zitten in een connector. Ja, ik weet niet hoe de dingen. Daar heb ik toen dat bordje voor gekocht om even te kijken naar de draait al aan. Net voordat ik met haar omdat je gewoon de pico kennis en je moet gewoon wat goed weten. Dat je hard werkt, dat het goed gaat. Ik denk wel een beetje kansen moet gebruiken. Dus dan heb ik dat toen dat
So let's conclude on this first part of the tutorial. We're getting started. I don't know if everyone could reach the reading of a sensor. So this is just an overview of a result application. So I created two handler functions for each. So I created two commands. Let's start from the end of the code. So there is my shell which is running at the end of the main. Okay. First, I need to initialize and set a few things for my drivers. So this is copy-pasted from the test application in Riot. Here I declare two new functions, so temperature, humidity, and the handler function, so it's a pointer function. And what is inside both functions, it's just checking the number of arguments is correct. And if it's not, I print the usage, so it's just okay. Then I read the value. So this is a trick to have negative or not values. And then I just print the value to the terminal. Okay. And to see, so I'm reading the solution. Since it's as a folder, I need to update the Riot-based variable. I'm saying, okay, build for this board and use this IoT-Lab node / terminal. So it builds, it flashed to IoT-Lab using the command line interface tool. It opens the terminal, so it's a resurrection. So you can ask, it's not there, but you can ask Gaetan all the magic behind this. If I type entry, so I see the prompt of the Riot shell. So I see that in my makefile I kept the PS. So there are just two threads running. One of the threads is the idle thread, and the second thread is the main thread. So it's the thread in which the main application is running. Okay. I can reboot by node if you want. And now I can read the temperature. So 22 degrees in the IoT-Lab site room. And the humidity. So 54% relative humidity. Okay. So it's quite easy, and you have something already ready. Okay. So do you have any questions on the tutorial, or is it, could you finish this part? Or? Okay. So now, just lost. Okay. just a few notes. You can go further and have a look at all the existing applications in Riot, so in the examples directory, but also in the test directory. So test applications almost are examples of how to use almost everything that is provided by Riot. You have test applications for all drivers. You have test applications showing radio drivers, package, everything, system. So it's a very important resource for learning Riot. So a summary of this first part of the tutorial. And now we will move to the LoRaWAN part. After, so the LoRaWAN part is here, LoRaWAN with Riot. Okay. But maybe before we can do a short break. Yes. Let's do a break.
So, just a little bit of context. So we have several IoT protocols, depending on what you want to do. In some cases, we don't need that much range, and we might need to set maybe more data. In some more cases, we need low power. So maybe like for smart homes, we might have some more dispersion on our networks, where we can have like higher traffic, low power consumption, and in some other cases, we might want to have maybe a bigger range. Maybe we're talking about transmitting data more than 10, 50 kilometers, even up to 100 kilometers, where we can have a low power mode, but of course we have to sacrifice a little bit the data rate we can set, but in some applications it can be really interesting to do this, and we're talking somehow about wireless wide area networks, where here we have LoRa, the technology that runs on LoRaWAN, and we have Sigfox and some other of this called low power one. So we'll focus on LoRa here. So what is LoRaWAN? LoRaWAN is basically, I would say, a framework, but it's like a series of technologies. It's a NAT protocol, is an architecture that was designed by Semtech, and it's promoted by the LoRa Alliance. This was released around 2015. They came with the first release 1.0 of the LoRaWAN specification. They are continuously working on this. They already pushed the 1.1 specification now in 2018. They're based in this LoRa radio modulation, which is a long-range technology, and also these kind of networks, as most low-power wire networks, they work in a star topology with base stations. So, just a few words on LoRa. I'm not going to go in details on how the modulation works itself, but just to know, it's a long-range radio technology. It works with this so-called chip spectrum. Basically, that's the shape of one symbol. It varies the frequency linearly, and this gives a really nice feature of being robust to noise. Also, it's really good for multipath, for controlling multipath effects and Doppler effects. So this could be used, for instance, for moving objects, and we're still able to decode the LoRa signals. And also, we have some control on the spreading factor of the signal. We can talk about that later. But basically, we have a trade-off where with some spreading factors, we can increase the range. But of course, that's not for free, because we increase the time on air. We will see later there are some regulations of time on air in the LoRaWAN specification. And also, the longer we transmit, we consume more energy. So it's important to know that there's a trade-off there. Yes. Okay. So an overview of the LoRaWAN protocol. As I said, it's an architecture. It has a network server. It has a lot of stuff. I'm going to go into details later. But just to know, basically, the idea is there's an application layer that can talk directly with LoRa MAC. This is a MAC layer of the LoRaWAN protocol that has several classes. We'll go to that later. This LoRa MAC protocol that runs on top of the LoRa modulations, and there are different sets of LoRa modulation depending on the region. Here in Europe, we use this 868 megahertz regulations. And next. And here, I've talked before, there are some regulations on the LoRaWAN, like access to the physical layer. Here in Europe, we have 5 groups of bands. They're divided in different. Bandwidth. It's 125 to 250 and 500 kilohertz. The important thing is that there's this time, like we have a time constraint access to the physical layer. That means like we have to respect our duty cycle. For instance, here we can see the duty cycles of the different bands. Like usually it's 1%, but we can have like 0.1 or 10%. That means, for instance, if we have a 1% restriction on duty cycle, if we send a packet that sends for 1 second, then we have to wait another like 99 seconds before sending again. Otherwise, we're not respecting the LoRaWAN modulation. And as I talked before, the spreading factor increases the time on error. So if we try to use a higher spreading factor to send a packet like next to a gateway, basically we're just wasting time on error. So we could then send like not so many packets. And in Europe, there are these, they say, 16 channels that we can use in the LoRaWAN. So how do we get the time on error? Basically, there are several tools available. We can always go in the MacGyver way and somehow to follow the equations from the LoRa Designer's Guide, but they require like some knowledge, and it's not a direct equation. So we usually try to use either the LoRa airtime calculator spreadsheet that you can just clone, and you can follow the link in the slides, or there's a new LoRaWAN time on error package. It's a Python package that's also really nice to estimate the time on error based on the payload and the channel payload spreading factor and bandwidth. So, talk before about some LoRaWAN classes. Basically, there's a trade-off between downlink latency and how fast we can, or what's the latency from sending data from a network server to a LoRaWAN device, and power consumption. I will explain this. Basically, for instance, we have the Class C device. This is like the device is always listening. So that means if we want to send data from an application to a node, the node will receive the application, the packet immediately because it's always listening. And if it's always listening, that means, of course, it's consuming more energy. We also have a Class B in the middle that I'm not going to talk so much about it because it's not supported by many LoRaWAN network servers. But on the other extreme, we have Class A devices where they can only receive data after they send. So that means, for instance, if we want to send data every 10 minutes, it's okay because we can be sleeping like the whole time. We don't receive any packets, and the network server has to enqueue some packets if we want to receive. And when we send a packet, then we have the chances to retrieve the packet. But of course, if we want to do like control or actuators, maybe it's not the best class, and usually we try to prefer Class C for that. And about the LoRaWAN network architecture, as an overview, we have devices. Like on one side, these devices talk directly to a gateway in the star topology. So these gateways are just dumb devices. They can only forward the LoRaWAN packet to receive, and all the magic is going in the LoRaWAN network server. That is the one who has to control all like a join procedure, confirming the messages, and all the LoRaWAN specification mainly runs in the network server. And also the network server can connect related to one or more application servers, where we can then somehow treat our data, save it to a database, or whatever we have to do with our data. And I will talk more about that, but basically these connections are secure. There are several symmetric keys used in the LoRaWAN specification. This is a more detailed diagram on how LoRaWAN works. Basically, we have the sensor that is so-called like a LoRaWAN slave, where you can send the data directly to the gateway, this thing in the middle. But as I said before, the gateway is just a packet forwarder. So it could be that several gateways receive, for instance, the same packet, and then the network server will be in charge of just picking one packet. as we can see here. And yeah, the network server will be like the LoRaWAN master who has control of all nodes connected to the LoRaWAN network. So okay. So how can we use the LoRaWAN? There are some existing LoRaWAN implementations in C. The first one is Arduino LoRaWAN in C. That is the one, maybe like a community is trying to use this one. It's the one that runs on Arduino. It was made by IBM like 3 or 4 years ago, and it's a maintainer. This is a branch made by some people working with Arduino, but it's mostly nearly unmaintained now. This runs the LoRaWAN 1.0 specification, and we also have the LoRaWAN node that is the syntax reference implementation. This one can run in LoRaWAN 1.0 and 1.1, and is used for certification on the LoRa Alliance. And there's some support in some devices, like Mbed-OS already has a like the LoRa node specification. We have also MicroPython implementation. RIOT supports LoRaWAN and minute. As I said before, these nodes connect directly to the network server, but these nodes are identified by a 4-byte address, which is only used by the internal LoRaWAN network. But we have some encryption layer between the node and the network server, but we also have an additional encryption layer between the node and the application server, so that's make it quite secure. And also there are some people that have a third application layer, because this application server is just a way on how to distribute or forward the payload, and there are some people that also have like a third layer for security that's up to the user. Next. And there are some like to join a LoRaWAN network, basically there are two mechanisms. The first one, it's possible to do over-the-air activation, where we asked LoRaWAN network to identify our node, and we receive the keys that we will use for sending the data. That's the first one. And you, it's more detailed here. And this is really good because a different set of keys is generated each time we join. And even there are some network servers that could ask devices to regenerate the keys, so it's quite secure. And there's also another called activation by personalization, which we can just hardcode the same keys generated by the join OTA request. And it's not that good for security because they're using the same keys, but it's really nice for running the LoRaWAN experiment. Next. So about the network operators. Basically, there are several network operators that can be used in order to connect to a LoRaWAN network. There are even some open source implementations, and we can even have our own network server. There are open source implementations we can run in our own server. So if we have a packet forwarder or a gateway, we can have a private LoRaWAN network. But there are some alternatives. We work a lot with the Things network. I will talk with more details later. Here's the Things network is a community-based project for like building a LoRaWAN network. Their software stack is open source, and basically people like anyone can just join by a gateway and give like the gateway to the community of TTN people here in Amsterdam. I know there are a lot of gateways around, so we should be able to pick a LoRaWAN like a coverage here. And it's really nice because there's no restrictions. In theory, we have to respect the LoRaWAN regulations, and now they're forcing that we have to respect this duty cycle restriction. But so far, there are no like a data restriction, so it's really nice for even running like experiments, or in theory, one could even run like an actual project with this. And also, they provide a lot of friendly APIs and application servers to deal with the data. Next. So let's get with the first step. We will set up the Things network account. The idea here will be to have our own application servers. And they're on IoT-Lab. There's one of these one of these gateways. So we'll be able to connect to the LoRaWAN network via the gateway there in Cyclane. Right? And you should be able to see the data you send in the application and the integrations that we'll be adding later. So the first step, you should create an account in the Things Network. This is a link. You can follow it directly in the 05 LoRaWAN with RIOT slides. And then there's also an option. It's optional because if you have a gateway, this is a console where you can administrate your gateways, add, remove, configure, and whatever. And after creating an account, you should add an application that will be the one we will be using for this tutorial. And also, you need to add a device to the application because like all nodes have to be directly registered in the application in order to get the keys for joining the LoRaWAN network. So all people got the link. So let's wait like a few minutes. If there are questions, let us know.
Then, if you want, like actually, I've been working like with different sort of implementation of this stuff. If you want, I can tell you there, like the whole procedure, like yeah, we can, yeah, we can. But if you want the whole with the details of how the user there, yeah, no problem.
There should be our HTML class slash main tutorial office JavaScript mit JavaScript. Weil das ist ja eigentlich, was wir auch noch sagen.
Nee, das ist ja irgendwie diese komische Weiterleitung nach Netzes, die ich nicht verstehe. Und
Don't forget to add the device to an application, otherwise you won't get the keys.
oh, warte mal kurz. Debugging. Ich glaube, ich habe den Fehler gefunden. Das ist ja eine Durchgangsknopf verlassen. Okay, ist das noch richtig? So, alright. So, was ist denn jetzt Toxic Pass? Was soll denn das?
One registered device.
Ah, so, jetzt fehlen hier schon mal Descriptions raus. It's all denied. Den brauche ich dann gar nicht.
I need to run the program.
Das ist jetzt ein Joke, oder?
Jetzt wird halt das fertig ist.
Und warum nicht? Wenn
Was someone able to
Elias schickt ihn doch
send
hier
it?
hin in das .cp und da liegt die drinne.
You can check the receipt data in the same dashboard from the Things Network. There's a data part in the application where you can track what you sent.
Wir müssen jetzt bei der Hauptseite, dann hatten sie da so einen Ausschnitt, wie das ausgesehen hat. Für den Nachbarcheck.
Bis hier unten ist es so. So, und deshalb, so sieht es ja bei mir aus. Doch. Aber das ist, ich habe es jetzt nicht in Home und noch einen Unterordner, aber es ist
klar. Achso, so.
Und Default-Händler habe ich ja nicht für Slash. Deswegen habe ich den ja hier oben gerade rausgenommen. Aber gut, ich kann jetzt auch mal. Ich kann natürlich das einfach nochmal pasten hier und einfach sagen für Directory Slash. Noch das gleiche.
You receive from the RIOT. Okay. So all the zeros was not all the zeros.
No, that is generated by the network server.
Do you know when do we go to lunch? I think it's the schedule says 12:30. Okay.
Kijk, hier wordt al nu komen we op het punt. Oké. Dus, we zijn hier.
So this test application provides you now you can try to register to join the network instead of those.
Not joint. De joint zijn, een gateway of zo. Joint. Ah.
Activation.
Just one comment. In the shell application, if you reboot the node and you entered your keys before, so if you reboot the node, it resets the RAM. The keys are in the RAM. So you have to re-enter the keys and rejoin again.
That'll be hard. Dus een joint. Je moet gewoon dit doen. Oh. Dat is het. Kijk, en nu hebben we het joint. Dus als ik nu dat commando dit heet, dit. Dit is wel een spatie. Dit is RIOT-OS. Deze bedoel ik. Ja, want daar zit natuurlijk dit keyboard er overheen. Ja. Als ik dat aan jou vertel, dan jullie moet je er gewoon echt zo ja. Ja. Niet overzicht. Vast testen. Maar er is nee, klopt. Nee?
Dit was de registratie.
Oh, dat is wat anders. Weer die instelling.
Very loose. En easy lock.
RIOT and then you can put the slides to
Lukt het niet om deze pasje te krijgen? Maar ik ben vrouw zien.
I can see that this is the message I sent.
Yeah.
Yeah.
Do you try to help us? Here's the factor. Yeah, it's it.
It's still waiting for the completion of the transmit.
No, I think it's wrong. You can try, I don't know what you can do is try to flash the node again.
Again, what?
Try to flash the node again. Yeah, I think it froze. I don't know why. You flash the node again and then you
Typing all the keys.
yeah, we just got that. You have to you can check it in the data.
Yeah. So in the IoT-Lab, there is one device allocated.
So you can data. You can check that's where they are. So now it's in the /lorawan/simple, and then you see how to actually interact directly with the code to send lorawan. So lorawan package.
Oh, wacht even, dus we hebben nog fouten. Kijk, dan terug naar kunnen we niet payload vervoegen. Dit is de RX. Oh, dat ding is echt goed. Precies. Dat moet je altijd tegen. Oh.
Join.
Niet dat iemand van alles over hem. Dit verzinnen we niet. Oké, goed. Feitelijk willen ze gewoon even.
Ja, ik denk
So there is a process in RIOT to be able to store the keys on the EEPROM memory of this node. So you can do a lorawan safe and even save the keys. So you go EEPROM they are reloaded you have something to do with but you can go to the next step. You can't store it. You can't store it because it's not merged. So what you can do now is in your application, store the keys at the state. You can create part of your code. That will be done for the next step. You can switch to follow this example. You will have an application that will automatically join to the network and start sending messages.
Actually, yeah. It was similar process, but maybe it was not.
We could try. Yeah.
Because you see the message arriving on the backend. It's just that the backend is reminding you, but you don't. So there is the errors window. It's not super reliable.
Of course.
Yeah.
So we are going to 25 yes.
Yeah.
Yeah. But so there is another thing. If it's using ISM band, we can also quickly program the radio aspect so they can necessarily.
Yeah.
You can start from the
solution of the previous example, just in case.
seconde. Oh, is dat 2? Sorry. Oei. Stop. Every 2 seconds instead of 20. Sorry. I have a sleep of 2 seconds instead of 20.
Yeah, that's why like the.
Yeah.
Yeah, I think that the person is correct.
Yeah, that we were blocked. Yeah. I'm ook op de fiets wil je de hei op. Engels. Nou, de eerste zin valt allemaal naar gemaakt door resultaat. Het verdienstpaneel kun je allemaal kiezen welke provider. Talen, advies. Google heeft ooit, Google is de enige die zit in kaart bij bol.nl. Nee, heb je ook Bing, Jan. Maar digitaal is dan zit je gewoon vast. Ook als je niet Google, bij Google is het gewoon factuur 2 cent. Ja, ik ben er niet. Er zijn nog zo staan. 5 vestighouden. Ja, dus je heel snel onder de webpagina gesloten. Dan moet het wel klein zijn.
ja.
Dit is voor het en ja. Maar dit is gewoon hier bedrijf. Ja. Ja. Nee, dat klopt. Maar dat snap ik gewoon. Je drukt op een knop en er werkt. Ja. Maar dit is gewoon waar alle pijn in zit. Ja, zo weet je. Ja. Maar dat is ook
Here it's channel.
En dit zijn gewoon
Channel. Happy with it. We don't know much about following that. Then the example, now what is a channel in the sense of Cayenne?
You define different channels for describing for instance, I don't know, channel 1 is dynamic, blah blah blah. Second channel would be like static.